Hello, my name is Will Barker, and I'm going to talk about some aspects of the strong coupling problem in gravitational theories. So what is strong coupling? Well, a gravitational theory may contain a propagating degree of freedom, which vanishes when you look at the perturbation theory around an exact background solution. And this is thought to mean that that background solution is dynamically unreachable, which becomes a problem if the solution is something that you actually want in your theory. So examples of this from the literature are given in higher dimensional Gauss-Bonnet theory, where the whole graviton can become strongly coupled on the background cosmology. There are also examples in Horava gravity. It's thought potentially that some of the infrared exact solutions are spoiled by strong coupling phenomena. Perhaps most famously in massive gravity theories. Massive gravity in the linear theory, it has this scalar mode, which is theoretically problematic, but actually there are strong coupling effects when you go over into non-linear completions of massive gravity, which apparently screen the scalar mode. Even in this case where strong coupling is thought to be beneficial, there are potentially some problems with unitarity, although this is quite strongly contested. So in this talk, I'm actually going to discuss so-called non-Riemannian theories of gravity. So non-Riemannian gravity, it doesn't just have curvature on your manifold. There are these other qualities called torsion and non-metricity. And the idea behind these is that you just extend your crystal symbol connection with some extra degrees of freedom, the so-called disformation and contorsion degrees of freedom. So general relativity in this broader non-Riemannian context is given by the Einstein-Hilbert action, in which the torsion and non-metric tensors have been switched off with these lambda multiplier fields. Okay, so I'm going to keep the non-metricity switched off in the talk, but I'll consider theories which may have some torsion in them. And when you've got torsion, accounting the fundamental degrees of freedom, gauge degrees of freedom in your formulation of the theory, combined with an understanding of the Poincare gauge symmetry, tells you that there are up to 20 propagating degrees of freedom in any particular torsional theory. These are decomposed in terms of their definite spin parity states here. So you've got some scalar, vector, and tensor particles in addition to the standard Einsteinian graviton. So what does it mean to have up to 20 degrees of freedom? Well, you can imagine a Lagrangian which naively has n field degrees of freedom in its formulation, but because of missing velocities, only m of those are actually propagating. So you can always construct your Hamiltonian by a Legendre transformation, but during that process, during the definition of the momenta, you find that actually some linear combinations of those momenta, perhaps with the canonical fields as well, vanish. And so these are called the primary constraints in the theory. And what that means is that even though you can always go ahead and define Hamiltonian in your canonical phase space, the 2n dimensional phase space of momenta and field variables, there's actually this constrained subspace on which all of the physical dynamics resides. So you can always construct an invertible Hamiltonian from which you can recover the velocities by the missing velocities by including these arbitrary multiplier fields, these Hamiltonian multipliers U. But you have to stick yourself onto this constrained surface in the phase space in order to recover the physical dynamics. So how do you stick yourself onto the constraint surface? Well, not only do the constraints have to vanish in the dynamical evolution, but their velocities also have to vanish as well, right? So the velocities are given by the commutators of the constraints with the Hamiltonian, which gives you this formula here, and the ramifications of this formula depend on whether or not the commutator or Poisson bracket between the constraint and the various other constraints in the theory vanishes. If it doesn't vanish, you can determine one of the Hamiltonian multipliers. If it does vanish, you end up with a so-called secondary constraint whose velocity must also vanish, etc., etc. So through this process, you end up with a collection of primary, secondary, tertiary, and so forth constraints before everything becomes self-consistent and physical. And the reason that this is useful is that it allows you to count the propagating degrees of freedom. And so the propagating degrees of freedom are given by this formula here. So propagating degrees of freedom is half of the dimensionality of the canonical phase space minus twice the number of first-class constraints. So first-class constraints, they commute with all of the other constraints, minus the number of second-class constraints, which do not commute. And so in order to determine the quantities on the right-hand side of this expression, it's clear that the Poisson brackets between all the different pairs of primary constraints, so-called primary Poisson matrix, is absolutely critical. And it forms this sort of theoretical barcode for the modified gravity theory that encodes information about the propagating degrees of freedom. So just to connect this back to non-Riemannian gravity and strong coupling, the Hamiltonian analysis was done on torsion field theories in general at the turn of the millennium. And it was actually found that generically you cannot activate any new torsion particle beyond Vainshtein's graviton without simultaneously activating other torsion particles which are strongly coupled. So this was a bit of a problem. It's become somewhat part of the doctrine of constructing torsion field theories, that you don't want to consider anything which isn't sort of a minimal analog of exact GR with non-Riemannian geometry. You can't cook up more interesting actions because you'll normally run into a strong coupling problem. So this is just an illustration of primary Poisson matrices as you go from linear to non-linear theories and their structure changes, which indicates strongly coupled modes becoming activated. So I want to introduce some new software which we can actually use to start to address these questions and then perhaps resolve strong coupling for torsion field theory. So this is the Hamiltonian Gauge Gravity Surveyor, or HiGGS. It's a package for Mathematica, the xAct tensor manipulation suite in particular. So you can use HiGGS to perform Hamiltonian analysis of theories with curvature and torsion, either in a targeted manner for a particular theory on your desktop computer, or if you want to survey a whole Lagrangian space, you can run it on a cluster or supercomputer as well. So I'll just give a quick example of how HiGGS works. So this is just an example notebook. So perhaps if I just demonstrate some of the degrees of freedom. So Hamiltonian analysis is done in the 3+1 or ADM foliation of space-time, where you split off the time-like direction. That's what allows you to do the, or allows you to discuss sort of energy and its conjugate time direction. And once you split off the time direction, this enables you to express tensors in terms of states of definite spin and parity. And so everything in HiGGS is represented in terms of spin and parity. So this quantity here, expressed compactly, is the spatial gradient of the spin parity 1 minus, so the vector part of the conjugate momentum of the tetrad field in the theory. So it's a simple thing to imagine, but if you choose to express it in terms of its fundamental constituents, so the lapse and shift vectors, the ADM formulation and the composite gauge fields, you can see it's actually really quite a complicated expression. And this is the form that you actually need the quantity in to perform the Poisson bracket calculations, which is why we need really computers to do the calculation for us. So how do you use HiGGS to analyze a particular theory? So this is a theory which is general relativity plus a single vector torsion particle. And you can see HiGGS can identify all of the primary constraints and calculate the Poisson brackets between all possible pairs of primary constraints. And it expresses them in a nice sort of compact covariant form as well for you to sort of just use in a pen and paper calculation later on. You can also calculate derivatives, time derivatives of the primary constraints as well, which is obviously what you need when you're constructing the secondary constraints and so forth as part of the Hamiltonian analysis. Okay, so just to return to the main body of the talk, how do we scale the analysis to supercomputers? Well, HiGGS is parallelized over the fundamental computational unit of Hamiltonian analysis, which is the Poisson bracket. And so the benefits you get from that parallelization, the restrictions on the speed up are going to be dominated by the slowest brackets involved in the calculation. What is it that makes brackets slow? Well, we saw originally, just in this example notebook, we saw how complicated the operands in the bracket could be, how big and messy those covariant quantities are when you're actually evaluating brackets. There are other things which make brackets more complicated than you might imagine. So in the Hamiltonian field theory, a Poisson bracket is defined according to variational derivatives. But normally you evaluate brackets between local quantities, right? And to express a local quantity as a functional, so in terms of variational or to which variational derivatives can be applied, you have to think of it as an integral over a Dirac distribution. And so this actually causes generically derivative spatial gradients of the Dirac distribution to crop up in the analysis. And the end result of this is that a Poisson bracket between two fields is not best understood as a third field, it's best understood as a second order differential operator. Okay, so now I'll just move on to some new physics that's come out of the use of this tool already. So I was interested in solving, or at least trying to address the strong coupling problem in the context of torsion. And my approach was to generalize the use of these multiplier fields by splitting them up and using individual portions of the multipliers to switch off or suppress irreducible representations under the Lorentz group of the torsion, the non-metricity, and even the curvature tensors as well, in a sort of piecemeal basis. There are infinitely, well, not infinitely, but very many ways of doing that many combinations you can imagine. So this theory, which I was interested in generically, is just Einstein gravity plus various second order corrections from the curvature and second order corrections from the torsion, but in which we were also switching off various parts of the curvature and the torsion as well. And again, the whole of the non-metricity is switched off. So how to actually sort of study this generalized model? Well, I took a model which was known to be strongly coupled, so not three models, actually one with a vector or two with vector torsion particles and one with a tensor torsion particle moving in the linearized theory, and in which strongly coupled modes are present in the nonlinear case. And I sort of asked Higgs to do the brute force Hamiltonian analysis of all 192 multiplier configurations of those three theories on a supercomputer. So this is a plot from beginning to end of the computation, which takes about an hour. And so there are sort of 14 nodes on the supercomputer. This is the Beta 4 supercomputer here in Cambridge. Each line here is the computational workload of a single core. Each color represents a particular theory. You can see it's just switching from theory to theory as it evaluates various brackets. So what was the upshot from this survey? Well, actually something really nice came out here. So a really nice little candidate theory of gravity for us to think about. So what this theory is suggesting is that you can take Einstein gravity, so the normal Einstein-Hilbert action, and add on the quadratic curvature corrections of that parameterized by some alpha coupling. And then instead of switching off the whole torsion, you only switch off a part of the torsion, the so-called tensor component of the torsion in the irreducible decomposition nomenclature. And again, all of the non-metricity. And what seems to happen when you do this is you don't actually invoke any new degrees of freedom beyond Einstein's graviton. And crucially, even when you go over into the nonlinear theory, you don't get any strongly coupled modes cropping up. It's still something that needs to be investigated a little bit further. But the mechanism behind it seems to be that because the multiplier fields don't have velocities in the Lagrangian, they introduce a bunch of new constraints into the Hamiltonian analysis, which through their own consistency conditions interact with the constraints of the original gauge fields through this sort of four-step process, which is quite robust against the introduction of nonlinear corrections to the theory. So what are the ramifications of this? Well, the theory basically looks like Einstein gravities, the Einstein field equations, plus some higher order correction where you switched off part of the torsion or of the non-metricity, and you actually determine part of the part of the torsion tensor that's not switched off in terms of the remaining curvature. So this is a nice, interesting Lorentz invariant and action derived theory, which doesn't seem to introduce new particles. So its phenomenology will be very interesting to study in the future. So in summary, you can't just get away with doing perturbation theory around exact solutions in a new theory of gravity unless you have a handle on the nonlinear degrees of freedom. These are obtained through a Hamiltonian analysis, and I want to emphasize that this can be done on silicon and at scale. An example being the Higgs package, which applies to curvature and torsion theories in gravity. And already from that, we have an interesting new candidate theory to play with hopefully more results to follow. Thank you for your time, and I would welcome any questions.